Sobieczky with Lost at Sea using random walks for scale spaces and sea surface satellite image analysis. That is one long title. So thank you, Florian.
Yes, thank you for giving me the opportunity to talk about this here. I would like to say that I enjoy this stuff a lot, and I have a very personal reason to be talking about it. First of all, I should say that this is joint work with Marilyn Waldman, and most of the programming we're going to see here is under her advice and guidance and refinement. I myself, I'm working usually with discrete probability models, such as random walks on graphs and on structures that are everything but continuous. So I would like to also say that I must remind you of the incident that happened, I think 1.5 years ago in June. The sailboat called Nina disappeared in the Tasmanian Sea around 6th of June, and one of the greatest searches ever in New Zealand was conducted, and these 7 crew members couldn't be found, one of whom was a computer science professor at CU, who in the Boulder and Denver area was very well known as an expert in networks and computer networks, and for her authorship in the book on system administration. So using satellite images, which is what this talk is about, you know, has recently gained a large demand because not only people who drowned or for whom one has conducted searches underwater with SRA technology have, you know, been missing, and the recent accident in airplane traffic shows that maybe also one should rethink about putting only black boxes in these vessels, I mean this aircraft. What if we just streamed the data to a satellite, what's happening in the cabin? I mean, we would be knowing much more. Anyway, the structure of the talk is, we'll talk about this after a brief motivation object called scale spaces, which is something that was en vogue in the early 90s in image analysis, because one started to experiment with nonlinear models, and they seem to suddenly be able, especially with the new computational power, to do fabulous things. And I will say what I mean by nonlinear. I will present a much simpler model, which has the advantage that even though no crazy things happen, it's a model where we have control over things, and we can actually calculate such things as scales and determine running times of algorithms. And this, by giving up the cost of these fancy things that produce the popularity. But if you look on the sample gallery page of Digital Globe, for example, this is the south end of the Golden Gate, and you see sea surface, and one of the things that is striking is, even though there is no single cloud, to make out a single object, maybe of the size of a person here, would be probably hard because of the structure of the rough sea. So boats in a to spot boats on a. This is from the same satellite picture. Here's a boat which we see immediately, and as you can see, I mean the sample page is about 10,000 times 10,000 pixels large. It's a GeoTIFF format file, and you can get all the information about the exact locations of the boundaries of the picture, and you would immediately recognize that as a little boat. Now, this gives you the idea that it's always good, whatever automated recognition system you came up with, then to still, because it's a picture, to look at the data yourself. And from what we will see, even though the worst thing is that you discard some data as not necessary to check. The false negatives are, so to speak, the big danger. So we want to really, in this case, look at, I mean, since it's a vast data problem, to, you know, given that for a surface area such as the Tasmanian Sea, you can have this data in every instant, or let's say over, in the case of the duration of the rescue, it was 3 weeks. You know, store this data and try to work your way through it, and we will see that we can't do it by just looking at it with our own eyes. It's impossible, and we will see how dramatic it is. What we will also recognize is that the data that you have about the sea surface is very special, in that it displays something natural, and there are some points in it which are, you know, artificial. And also in the 90s, or more when there was the transition from the old JPEG codec to the new JPEG codec, that suddenly used wavelets, when the big image data compression discussion was very high, one realized that pictures of natural scenery has very specific, you could say, if you consider it as a function on the plane, very specific derivatives, not in particular how it's shaped as a specific realization of a process, but how often certain derivatives occur. So if you went through the whole picture and always took differences, consecutive gray values on such a picture, then you get a distribution which looks just about like that. So not at all Gaussian. This is, you know, let's say if we have gray values between 0 and 255, so we transformed the picture into an 8-bit picture, and we took differences between the picture at point x plus 1 and g of x, and x are 2 points, let's say, in horizontal direction in the picture, then this goes between minus 255 and plus 255. And this is a very typical, it's a generalized Laplacian distribution, which one can observe and one can measure through different kinds of, well, for example, you know, you will see a picture about a tree with bark on it, and it has very much this kind of distribution. And if you take a picture of a wood, then it has that. It has slightly larger distribution because the differences are higher. But as soon as you put an artificial object in it, like a house, or something with surfaces that are plane, what you observe is that these differences collapse. It becomes more, well, actually, it also does something else here on the peak. So it goes away from the Laplacian form, and this is an observation, and one has, you know, speculated about its reason, has come up with certain explanations. I don't want to get into it. The nice thing is it gives us an idea of what we can probably do to detect artificial objects in the picture. Yes.
What is the goal here? Is it to find a boat on the top of the surface or a boat that has sunk to the bottom? Or
Only anything that you can see from above. So no, only sea surface. Maybe
okay,
like,
only surface.
yes. So maybe, you know, a yard underneath the surface, but anything that you would see from a satellite.
Well, it's really looking for something that's interesting, that's unusual.
Well,
And so it doesn't matter whether it's the surface of the sea. If we have some new sensor that lets us see 10 miles into the Earth and we can see, you know, Jules Verne land down there, we would, I mean, that would be interesting. So, I mean, what this is saying, there's something interesting, and it's trying to intersect the ability of the human with the searching capability of the machine.
right, so for example, you would have a type of anomaly algorithm, search the images and then come up with anomalies, then the human would come in and focus in on those anomaly detections.
Right, and hopefully those anomalies would be sortable by how anomalous they were. And the human would then, based on the intersection of the data, where they are and what they know about the environment, choose which ones to look at first in this kind of, you know, where's the boat search.
Right.
I do have to say though that I am specializing on the very special type of picture, namely satellite pictures of the ocean.
Okay.
And that's very specific. I mean, but it does have this distribution in its derivatives. And yeah, it's so to speak, lucky that usually one doesn't have very many boats on the surface.
Right, that's the great thing about this
Exactly.
problem domain.
Yes. So it's a very special problem in terms of the kind of picture data that one has if one sorts it, you know, if one looks at this type of distribution.
So you have a picture of the blank sea and you come up with, here's what the distribution is, blank. And then you can find an atypical point
Yes.
based compared to the blank.
Correct.
By running the derivatives and getting the math.
Yes,
It will
right.
kind of
That's
pop up,
basically
yeah.
it. And yeah.
And that's why you're focused only on the sea surface, is because you understand what that
Yes.
distribution under these weather conditions
correct.
would look like.
That is right.
Wouldn't it be a Mandelbrot fractal?
We think. It would be interesting to look at the distribution of the derivatives of a fractal image, yes. I wonder if that still is artificial. It would be very good. I mean, see these things,
Yeah.
I like this picture because you can't really say, is this now artificial or not?
Yeah, boundary.
So, okay,
Sorry,
so, but you were right.
You're looking, in the case of when something sinks, you're looking for the absence of a boat.
No, I'm looking what comes up to the surface.
The wreckage.
Oh, got it.
Floating pieces.
Yes,
Right.
debris from airplanes or a life raft,
Got it.
stuff like that. So it's really only sea surface stuff.
But I imagine there are a lot of false positives.
Yes. And what we
Right.
can about say is that we can take this huge data set and crunch it down to 10%.
Right.
Yeah. What to ignore.
Yes. And then it starts to be risky, so to speak. So this is the search area for this particular boat that sunk, probably. And we have, so, you know, a area of 500,000 square kilometers. And a single geotiff file that you saw, you know, in its resolution before with the boat and the Golden Gate Bridge has 10,000 by 10,000 pixels corresponding to 3 square kilometers. So you have 61,000 such pictures. And what I will show you I'll do is that I have on the order of magnitude 500 by 500 pictures that I deal with in my app to work my way through it, which if I can work on this thing for 1 second and then be done with it, it will take me a month in this area.
How frequently do you get new images of the same area?
Yeah. Possibly.
Twice a month.
So
Yeah.
something I will not show you is the confidential data I have been getting from the family of the people who of this lady who was on this boat, and over a period of 3 weeks I got a chunk of data where about twice a week the area was covered.
Okay.
So I have about yeah, that makes sense because we calculated 1.5 years to dig through everything.
So out of curiosity, do you look at those deltas as well? Or what's changed between each snapshot of data?
3 days.
I mean, do you look at that also as a way to find features?
I know.
Okay.
I mean, in the moment, the real goal is in the way to make this a general. I mean, to find the real formulation of what one is really looking for, and maybe I can jump ahead to that. So you have an idea how it's coming to. See, we don't want to miss anything, so in the critical cases, we still want to take a look at it. The idea would be to make an app that gives you everything that might be something interesting, and then in the morning, after you kind of work through the whole night, you kind of watch a movie and you look very quickly through this. So you hit stop when you think that would be something.
On a side note, you're familiar with Galaxy Zoo and those open source efforts to do the same sort of things for galaxy classification?
Oh.
It's just a different way of approaching the problem. It would be interesting to look at that. So you
Sure.
could sign up for Galaxy Zoo and they will literally just ask you and farm it out to millions of people to classify galaxies all day long.
Yeah, I would like to know if this distribution is in the background there.
Yeah.
But that's, I mean, you could do this. This seems to me
As a way, they're
Generalize
if I recall, they've added new projects as well, so it might be a way for also to validate your approach as well.
Yeah, I mean, in general, any class of images could be somehow approached in this way, as long as you have some idea of what's typical. And we'll see what I mean by that. So I would like to just let you see
A lot of math.
this thing called scale space. So what is it? It is really something that here's an image, and an image is a function from the domain of pixels that might have a difference in distance of epsilon, and you might be restricted to some frame around it, and you're mapping that. In mapping one picture to another one by filtering out certain things so that only things on a certain scale are apparent on this output picture. Now you see I have put 2 S's here because the way I'm going to use this concept is, well, what's coming in here is always the image that you work on step by step. For example, you can do something very canonical example of a scale space is the Gaussian scale space, where you perform a convolution with the Gaussian, of which the variance becomes growing in time. But if you lose the information after this convolution, you lose all the information about the fine scales. And the Gaussian scale space, as special as it is, and as much as it has been studied in the 90s, in the framework of certain axiomatic lists of properties that they should fulfill, and it came out to be somehow always the unique one that fulfilled all the axioms. It is not very practical in this specific problem. So what one drops, if one just asks for a convolution, and really wants to work with it in a realistic way, as the first thing is the translation invariance. So if I have if I look at an image and apply this convolution to it, and then shift it, it's the same thing as if I would have first shifted the picture and then did the convolution. Now, if I, however, define my operator that acts on this picture here, and then spits out a new picture, and the kernel is not translation invariant, maybe depends on the initial picture, then translating here, I would have to also translate the input, the reference picture with which determines locally how much, let's say, blurring or annealing or maybe reinforcing is going on. And this is something then where one cannot say convolution is a very handy and very symmetric transformation. What I would like you to think about, I'm using for this phi t is the following. Suppose you have this image, let's say, which has certain boundaries between regions that are typically of different gray values. And let's say we're superimposing on this picture a lattice. Well, in fact, that is usually how it is given to us as a digital image. It has the lattice structure. And let's just for the experiment remove, so to speak, of this graph, of this lattice graph, the connections, the edges between vertices of which the corresponding gray values differ by a certain amount. Now, what you obtain is in general, disconnected graph. And the amount by which they should differ, so that this should happen, let's say, is a threshold. And let inside these domains that we get in this way, a diffusion take place, which is just like heat conduction, and which, so to speak, if you let it run sufficiently long, will distribute around this region, but it will not cross the boundary. For example, it is in fact so that the convolution with the Gaussian, if you have a completely homogeneous lattice, will really model heat conduction on such a space. Now, what I like to think about is use the boundaries that come from the initial image, and then still run heat conduction on this one, heat transfer between nearest neighbors in single steps. And then you see, suppose there is some specific form of the boundary here, and suppose you would like to know what, instead of the gray value you have here, you should replace, you should take instead, you would like to know what, gray value that was here initially should be there now. And what this means is you make an average of the neighboring gray values, of those neighboring gray values to which the heat could conduct or migrate. And doing this at a short time means, taking the average over very close neighbors, doing it over a long time, collect, so to speak, the similar gray values in the same domain and replaces the average, or the Gaussian average, so to speak, on this unhomogeneous structure with the former gray value there. In this way, different gray values become very much alike if they're very close. And this is kind of the smoothing effect that this particular scale space has. That's what I call scale space with random walks, because at the bottom of this, there is a random walk, that kind of stochastic process that governs here. It's like the Brownian motion on a lattice. So back to our, so for example, if you compare the row of pictures up here, this is the scale space that you have in GIP, in the graphics manipulation program, that allows you to, well, for every vertex you do use a Gaussian kernel, but the variance of it varies depending on the local variation in gray value. Which is, if it's very high, then the half width of this kernel is very small, so that corresponding integration just for that point gives a very similar structure here, a similar gray value. Whereas if the variation is not so big in gray value, there is this smoothing going on inside the region. However, the random walk that we just talked about is different in that it is more sophisticated, in that if there is a boundary, it really will not, transgress, not go over here. Whereas this kind of GIMP feature looks over here and says, okay, no, if I'm taking this kind of support of my averaging kernel, that would be too large, so let's make it smaller so it will stay in here. That means here, very close to the boundary, there is not very much smoothing going on, which is the deficiency that you see, that here there's no smoothing going on at all. Whereas here, the random walk gets to all the different spots and still performs the smoothing. Okay, just make out that difference. I mean, what I'm talking about is that here the grizzle remains, even to a degree where here the smoothing already takes away some feature, whereas way much earlier in this kind of random walk scale space, the smoothing is already sufficiently done while these features are still here. Does that make sense? So I'm just saying it's a great scale space to use also for pictures, for denoising. And as you could see, for this particular application, one doesn't, so what one could say is, one tries to get rid of the detail of the initial picture that corresponds to the grizzle. One is only interested in detail of the picture that is on a larger scale than the salt and pepper noise. Okay, I would just like to mention very quickly that in medicine, another random walk scale space was very successful. The doctor gets a picture like that and draws with his pen these things and says, okay, here there should be its own segment, and there should be its own segment, and there. And then what you see is that corresponding to these labels or these marks, each one of those will have its own segment. So the way to achieve it is let diffusion take place, and if this is the label that it is most likely by migrating around hitting first, then the corresponding averaging belongs to the segment of this label. And the nice thing is, doing that, all the different so-called segments, the segmentation problem is an unsolved problem, because there's bottlenecks between the different segments, and they're all really almost surely, almost not connected, almost disconnected. But still, so in other words, with some probability, a migrating particle will move over here to the other one. And however, with this distribution of labels, it will not be as likely to reach the label belonging to this other segment. So that's why, and so with this method, even though we have not this nice scenario that I try to draw here, I mean, it's very likely that by choosing a threshold that is too small, I just get a whole disconnected, connected graph with only one connected component. I would like to just point out that the random walk concept has found other applications. Here we now have this kind of distribution for the so-called wavelet coefficients. the wavelet coefficients of the simplemost wavelet. A wavelet is a function with which you can generate new functions that look very much alike, and idealization and scaling are transformed from one into another, and which altogether form a complete basis for a space of function that with which one can describe the picture. So these are functions that are very much localized, that are, the support is very much focused on a point, but they can be translated, and that will be another wavelet. In particular, there's a wavelet that corresponds to taking the derivative, exactly this kind of difference. So if you just look at a function, you can say it's made up of its symmetric and antisymmetric part with respect to the value of the neighbor. And this you call, so this is really the derivative in discrete terms, and this will be the average. And you can continue to perform such differences in averages over different scales, and it's basically also a scale space. So again, the difference of the two gray values has this distribution. How can we use it? So if you look at this particular distribution here, where one just on a big 512 by 512 picture went through the differences of gray values, and whatever the value one formed this histogram here. If you compare this picture bar, which is this one, with all of these, particularly this one, you see that there is a collapsing taking place of this fairly wide distribution to something which indicates smooth surfaces and flat artificial parts, man-made parts, so to speak. And so how can we use this? There's really something that in the pictures you have seen where the boat was in, we would like to, I mean, if we find it, immediately give it to that 10% of things that we should still look at. Namely, where there's after smoothing even such a distinct gradient change. I mean, a change of gray value and a distinct gradient over a certain range. And if you think of it in the sense of a one-dimensional sub part, like for example, if the boat is here, and what you would do is choose little squares, and for each block run through the horizontal part, and then if you get across this change in gray value here, you would say, oh, this block is important. Let's save it somewhere else. That's basically the approach. And the idea is to run on a line and check if these profiles occur. And as you can see, it's not only the increase in the gradient that it's important, also how far does this proceed? So there are really, for description of a real feature like this, two parameters that are important. This is from the search for the Malaysia jet from last year. There are newspaper articles about this being possibly a life raft or something, a debris from. And I must tell you, when I saw this, I wasn't excited at all from the comparison with the pictures that I got from Digital Globe. There's tons of stuff like that out there. And if you now try to run this and just check for these flanks, these increases in gray value, you immediately get you know, with the cloud here, such a result, and you could just easily throw out 10% of the data in this form. Unfortunately, probably the image was pre-processed when it came into the newspaper. Unfortunately, the data is not usually like this. So how does it look usually? Here we have something which may not be so, you know, these little white things are wave crests. And if you look, this is a very big picture, and I think I should have magnified it more. Run the same program on this picture, and as you can see, failed to find one of the really important features.
How large an area is
yes, that is exactly about let me think. See this 3 no, it's not 3 kilometers. It's 500 by 500 meters. Half a kilometer by half a kilometer.
So you make adjustments to your algorithms for environmental factors such as a windy day when there's a lot of wave crests?
Yes.
Or a lot of crowds?
That's exactly the story as it goes on.
Yeah.
So, I mean, as you can see, it doesn't work because you will find gradients that are here due to maybe even irregular noise in the transmission of the picture, and the accumulated such changes. So what I'm looking at is the sum over the changes in gray value between consecutive neighboring pixels inside the box. Now do that for each box. The ones that come out strongly can be somewhere here, not at all here. The reason why this seems unbelievable is because this is so white. Well, this is all very constant white here, so the gradient is not so large on a very big part of it. So what to do? If we look at a so-called bit plane of the picture, these are the second last significant and third significant bit plane, which is, if you look at the function as a number between 0 and 255, you know, breaking it down into its bit structure, where these functions here are just either 0 or 1. And I've picked out from the sum a picture that I call G hat. It only runs from the lowest and the highest bit. And it is, of course, well, if, for example, L is 2 and H is 3, couldn't be, because B is never larger than 1, couldn't then be larger than 2 to the H. So I scale it, and that's why you see this increase in contrast by the factor, so that the largest possible gray value will be loose.
I'm sorry.
Actually, quite nice. So I divide by that largest possible bit and then multiply by the largest possible gray value. So this is this function that is associated with such a picture. And it's interesting what happens under smoothing with a different bit plane. These are very, you know, the bit planes 2 and 3, so they're rather not so significant. If you took them away, the picture would look very much like it. If you run a smoothing everywhere in this picture where there's a, you know, a dot that's not black, then you would very quickly, in a few steps, get a constant here. I mean, the least significant bits have this property that if you look at them as a picture itself, they almost look like noise. In fact, they are not. They're highly correlated. But still, if you ran a smoothing on that, it will immediately turn gray after a few steps. So that explains, if you walk from a picture with a lot of, you know, natural structure under smoothing to the corresponding result from the scale space, because this information that's about the detail that's encoded in the lesser significant bits gets turned into a single constant name, and is then result for the lack of, so to speak, natural structure. That explains the collapsing of these distributions. Now, how can we use that? If we run our smoothing, and then so if we run the smoothing first on the picture, and then only consider the second and the third bit plane, the second and third bit planes looks like this. So you see that all the detail has been annealed away. And however, here, and here, there was something that remained. And the reason is because here the smoothing didn't take place because of the high, carefully chosen threshold, such that by the smoothing here the detail would remain there. Would remain to be there. Also, another thing that's important is, so you can see the result is that we did discover those three books now. The kind of picture that we have here, the original one and the one that we have if we only look at the bit planes, now allows us to do the same thing as before. We go across horizontal, let's say, direction in a single box, and we discover a lot of gray value changes in that box still, and not so much anywhere else. So this is what's behind it, and what you see is some pictures of the app. You can then focus on that and look at all the statistics of that particular box inside the collection of all these boxes, then refine your understanding of what the real features are of these things, and maybe tune your parameters accordingly. So I could now perform a long calculation, but I think I shouldn't, about why it's, so what I could prove for you is that if we look at this thing here is the L1 norm of the discrete gradient of the picture inside a box. So, and this G is restricted to one specific box, this one. So, box I. There's many boxes of those. What I can show you is that the discrete gradient of the annealed picture, the one from the scale space, that I get if I run a random walk transition probability matrix on it, and look at it as a vector that changes under these transformations. In the case of the bit plane image, which is the one that only considers, that looks like this, is less or equal to some constant alpha times the corresponding discrete gradient in that box of only the smooth picture. So this P to the NG, look at it as if you had, let heat run along the corresponding homogeneous regions, and do the same thing. Do afterwards take the bit planes, that's something like this, a quantized picture, and look at the gradient, and you will find that under statistically speaking, for this group of pictures, this alpha here is relatively small. So in other words, when we have pictures where the lesser significant bits are all these grizzled pictures, for one, which means that annealing will make them constant very quickly, and that these lines where I have changes in bits that are significant, these boundaries form a lesser dimensional space than this space. So that, you know, the pairs of pixels where these changes occur are few compared to the whole picture. Under these two conditions, alpha is small. And that means if you have a false positive, like we have over here, and here, and here, by this constant, it will be, this constant will make it so small that the comparison with the other boxes, it will not be one of the first. These are always the first 5 squares, the first 5 boxes where this norm is large, but it will go down and be, so to speak, small enough so it's among the one that come after number 5, and we could say that when this norm is already small, then this is also small. So it will not produce new false positives, this process. It goes in the direct direction. That's all I can say.
But you really want that, right? You don't want to go off in false goose chases for
exactly.
When you're, I mean, that's a
right.
super important property for this kind of.
Yes, and I mean this, you know, these properties, how much they are present, that makes this thing small. You could numerically easily estimate how much they are there. Mm-hmm. So you could express this constant in terms of statistical data from this picture in the beginning, and then have with a certain probability corresponding to those frequencies that these, you know, they can actually change here, etc. Express your statement. So this is in the company Texas EquiSearch, found in, actually in September they found this like a ghost chip, and it is exactly the size of the Nina, and only 3 weeks later the media knew about it, and I'm not sure about whether that was also the delay for the rescue team to start hunting for it. At any rate, the rescue team decided not to go and look for it. I mean, they said it's not reasonable enough. Chances are not high enough. So then you can imagine that the families were in particular very non-understanding, and to a long time after, even after a year, they still did things on their own, such as fly planes out there and look themselves. So that's kind of the story. You can see here the importance of the scale space, the whole thing just with gradient and with the quantized picture, but without smoothing, and you're actually missing the ship here. And using this smoothing makes the noise be in the lesser significance be reduced sufficiently so at those points where the smoothing did not take place, these become prominent enough where the gradients will change. Yes, I think that's it. Yeah, I don't have any more.
And that was 3 weeks after
the discovery of that picture. And then the families got together
discovery,
again.
I mean the actual taking of the picture.
Oh, yeah, I think so.
Okay.
It's incredible with what legal and security-related issues one meets if one tries to, talk to private companies that have this satellite data, such as the globe. And I'm being very careful not to expose anything that I receive to work on, because I mean, the files that talk about the copyright are at least as large as the pictures. So it's
I don't understand what's copyrighted.
Their ability
if
to
you
think.
make a picture of somebody out there who's maybe sitting there and sunbathing, if it's something like that, or if it's
Well, what's the source of these images?
this is digital globe. I mean this one was Texas EcoSearch.
A satellite image?
Yes.
Yes. Whose satellite?
So,
I don't know. I mean, I got this out of you can see it in the corresponding. There's, if you type in Nina ghost boat found, you find many such sources. So this is a publicly available picture right now. But if you go to Digital Globe and they for some reason give you a picture to work on, then there will be some rules as to how far you can give that away. Michael, you should be the person who knows about these things.
well, the question is, who is going to sue you?
Yeah, I would.
Right. So if the probability is near zero, anybody's
question
going
is,
to
are
sue
you
you.
gonna
Why
find
would
that
you
out?
even worry about a copyright?
Well, we're monitoring this, so.
I mean, and I think the purpose of this is to potentially find
Yes.
and save lives. So
That
I
is
think
correct.
that there's a
Well, the military has satellite equipment that is probably, they don't even want to expose how good it
yeah, I
is.
think that's the big issue. Well, a couple of issues. One, you circumvent everything here if you put some well-placed sensors on the boat that will send out signals, right?
Lasers.
Right? A simple, cheap,
Football lasers.
yeah, signal-emitting sensors.
Yeah, but it's not the data over the whole region. See, I mean, this is imagery about, I mean, potentially somebody who complains about this is like Google Pictures, who can sue the company for being, suddenly randomly taken. It's incredible how few people are on Google Maps. Have you observed that? I mean, on
I don't know,
on
they
the
got
other
it.
pictures, they
Well,
can
then,
get
yeah,
the
like
right-
a Gaussian blur on,
Yeah, they got
so then
it.
they don't have to worry about it.
I see.
Yeah, but they got both my dogs. They weren't
So
scared
your
of my
dog
dogs.
should sue them.
Yeah, I'm very unaware. I mean, I really don't know. That's why I didn't put anything up there.
Well, one thing, if I may add some context, because I know about this a little bit, not as much as Florian. There was a huge storm, a massive storm around New Zealand, and they made the fateful decision to continue to sail out.
Yeah.
So they sailed into this massive storm with knowledge of the storm. And then there was, correct me if I'm wrong, a radio call that was recorded from Evie, the person on the boat, to the New Zealand authorities, saying we're in the middle of a storm, we're in trouble, we may be going down. So I think that's fairly strong evidence that the boat was gonna sink.
Good example. The time it took until the information of where exactly that call was made from, I think it was from her phone,
Right.
took longer than after the rescue team went out and looked for them. And then they found it was ridiculous where they looked for. They should have looked somewhere completely different. And this is the legal situation in the telephone company, that they wouldn't give out where that came from.
Wow. But couldn't you use statistical inference to estimate their location? Because you knew the time, because you have to log entries into departure from port.
Yeah.
The storm, the winds, the currents, that's all data that I assume you have access to, correct? Well, and then you can narrow, because it seems to me you increase your chances of finding any potential debris if you the narrower range, right?
That's what the search party would have done, though.
Exactly.
Right. So my question is, under what rationale did the New Zealand search and rescue team say there's not a high enough probability to go
Right,
investigate that?
Yeah,
particular-
because they looked up their stuff and said, no, it's over
Right,
there,
I'd
but
like-
the picture's
yeah.
there, we're not.
But, do you know that?
There's a lot of that information in the blogs and in the articles, but that particular one about the phone call is and the one about the ghost ship, so it came out only very late, much later than it would have been of value. I mean, they at the time they were overwhelmed with the efforts that were undertaking this family, and they were saying that went way beyond their expectation. But much later it turned out it was helped in the wrong direction. I mean, it wasn't the right place to look for. So.
Did they ever find the Singapore jet that they said they thought went towards Australia?
Of this year, yes. The one from January.
Malaysian, you mean the Malaysian?
The Malaysian, I'm sorry,
Sorry, 2014, yes.
So that's just amazing.
They
But
found it?
No, they didn't
they
find
haven't.
it,
Oh.
no.
But didn't they find the black
Yes,
box?
I thought
No, they didn't find
They had an
anything for
idea
that
it's a
one.
black box.
That's the more recent one that they
Right.
found the black
Right.
box for, the one
I
that
see.
was a couple weeks ago or something like that.
Yeah, so I think a simple fix, I mean, I'm a big backcountry powder skier, I wear a transmitter. I mean, I wouldn't go without it because, there's a reasonable chance I'm gonna get hit in an avalanche and I want them to find me and dig me out.
There's a lot of other factors that, I mean, on a big modern airliner, there's a lot of people flying on, there's a lot of other factors that come into putting sensors on those. I would think, and forgive me, but he said, just share the data. So the company I work for is DoD, and I'm on the health and civil side, but it's like, wow, how would you have transparency if it's all military data? Wow, that would be.
Poorly.
Yeah, it
So
doesn't
it's
happen.
accurate transmitter.
Yeah.
I can't say that I understood all that math, but so you were going from one way in that you were taking natural features and trying to smooth it out. Could you go the other way also and say we know what what wreckage might look like? Could that help to?
Yes, in a way, yes, because, for example, I mean, we have this picture, for example. It would be great. I mean, one knows from the dimensions of the satellite image that this is the right size of the picture. That's why it was so prominent. And as you can see, on that, this is the original picture. You don't see much else than a white cloud there. And what you could do, and that is actually one of the famous spaces doing more or less fitting of the pattern with the help of morphological operations. There's a scale space that corresponds to that. And you can then do pattern matching. But this is on a level that is one above satellite, where you are actually recognizing the feature. I'm trying only to filter and reduce the data volume.
You kind of, you have, I'm sorry.
Yeah. So just an interesting side note, I was at a party this weekend and ran into somebody who was doing this from the other side, which answers your question about why aren't the ships using transponders. They were trying to find illegal fishing boats. So they're using a startup that's doing this kind of thing, but to identify illegal fishing operations specifically. So they were launching their own satellites and doing all this kind of stuff.
Yeah.
So there's a lot of individuals that don't want to be found, which is the other counterpart of this.
Right, right, sure.
Quick answer, the boat had this rescue beacon that all the boats have, but in the case of this boat it was manually operated.
Yeah.
Oh my goodness.
No, see.
Which why?
It's an old boat. It's a very old boat.
I mean, it's therefore probably that something very sudden happened.
Yeah.
As Eddie said, it's always possible that you hit something.
Yeah, that guy that had to swim 9 miles from the ex-football player that a couple weeks
Right.
ago, he just fell over suddenly too. He didn't have time to activate anything.
Yeah, I think that could have happened.
So you have an upper bound on alpha right there?
I can
Yes.
make it.
Is there a lower bound other than 0?
Um,
And is it, can you then do, squish it to something much more specific?
Sure. Yes, there is, because together with the information of how much is still left in the image after the smoothing.
Right.
So the smoothing took not place at certain places, and you could easily check that in a linear time of how much volume is still in the picture that is not.
Does it help anything?
I haven't looked at it at all,
Yeah, okay.
but it's of course a good question.
So your derivative can reduce noise by increasing homogeneity of pixelation, and then creating a selective quadratic function. So have you used that post-processing to, or can it be done in regards to support vector machines and classification? I'm asking because Kaggle right now is doing this competition in regards to oceanography and trying to identify if an item's within a classification of 30,000 pictures, so if an object's plankton or a fish or shark and whatnot, so they have a better understanding of oceanography, density and whatnot of those objects.
Okay.
But I'm wondering but there's always that noise in there, so if they're trying to
Yeah.
get to the plankton level.
I think the answer is yes, because actually I forgot to put that up on the slides. The open problem now is the same thing with a different wavelet. When they looked at compression algorithms, they looked at specific pictures and how they are typically organized, and then designed for that specific picture a wavelet that would capture a lot of structure, so that very soon you would have all the information, and the higher subbands you could just drop. This is of course the simple most wavelet you can think of. And, going further and looking for very particular forms would then mean, if you have a little bit, in this case you could already do it, the chance to model already and focus on what you're looking for. Yeah.
I mean, have you done it with this algorithm, in regards to this, where you could write a Python script and say, running all 4 of these different functions, pick the one that tries to identify the object best?
That's kind of what I want to do with this app.
Yeah.
The idea was to be able to determine criteria for what to look for. And so far, we get these pictures and we adjust the threshold for the smoothing, the number of steps, how much should be smooth, and also which bit planes to use. So those 4 factors, so far have been obtained by playing around and seeing these are the best, obviously, somehow like that. But of course, in the moment, the class of pictures changes slightly. That will be different. So yeah, it should be possible in the direction of modeling using more sophisticated wavelengths.
It just seems to me the data science answer here is that you just force these boats and planes to have sensors and transponders. Because it's cheap. It's cheap, and then the data gets collected, and then develop processes to then discard the data. Because once you get to this level, the probability of finding anything is very low.
Yeah.
And it's how much time have you spent on this?
A year.
Yeah, I'm sure it's a great exercise and you're learning a lot,
Yeah.
but you would agree with me, the odds of you finding anything using this method is maybe 1%.
Right, at most.
At most. So again, that would be that you would tell your client, this is what happens, therefore it's better to spend the money on the cheap sensors and collecting the data in a process, right?
But that also means in an ocean, which people aren't monitoring that often. You have to have
No,
at
it
least
just
three satellites
pings up to a
triangulated.
satellite.
Yeah.
I
And
know,
you're
but
gonna
you
have
have to have
to,
at least 3 triangulated.
Yeah, to get a spot on the Earth.
Yeah,
And
okay.
keep in mind, there's multiple purposes for this kind of analysis, right?
Yes.
So what's interesting is if you're able to say, look, we've encouraged a number of ships to carry these monitors, but there's other people who also want to look for smugglers or what have you. And so in addition, we have a process like this, and it's multi-layered, and we first run a very, very fast algorithm with low false negatives, and that tells us where to, we take the results of that, and then we look at how far away things are, or we look at historical data, and we kind of combine things, and but the net result is we get to prioritize what we want to focus on to just that 1% that's most valuable, and then we maybe follow up with additional analysis.
I agree, except for if you have other viable alternatives. For example, if it was viable to have an intelligence operative stick a sensor on the smuggler's boat, and
what about those dolphins?
Yeah, the dolphins.
Oh,
Thank
yeah,
you. Right. So I guess the data science answer is yes, you're correct, and I agree. But there also look at alternatives, and then there's a cost-benefit analysis.
Yeah.
We don't. Your client doesn't have unlimited funds to spend. You have to look at that. And then what are the odds using this method you're actually going to find a Somali pirate ship? I would have
It's
to.
more scalable than sending out a research team in the case where, or not research, rescue teams in the
Yeah.
case where it doesn't happen, right?
Right.
You gotta weigh that cost as well.
Yeah.
CU
So
Boulder,
if this is implemented and works 1% of the time, that might save you a fair amount of money versus sending out rescue teams.
That's a good point.
It might
Yeah.
be cheap,
Okay.
like the cost
Fair
benefit
enough.
analysis.
so the CU Boulder engineering department has a team that works on saving rhinos from poaching, which recently has gone up dramatically because rhino horn is an aphrodisiac, and you can't convince many people in this world to use it that way, and the rate of catching people who actually shoot rhinos and cut off their horns and sell it in the Kruger National Park in Tanzania is 10%. So they're flying drone planes out there, and this is a potential application. So I put this picture up now in the hope that nothing bad will happen because it's confidential. But I would like you to see this smoothing happens, and this is a picture next to the one this one. So you can use the nature here and work on it and extract the speech very strongly. But yeah, one word about processing time, maybe. The smoothing works very nicely. It's a linear time. For a big picture, it's in an instant. The application of finding gradients for a 500 by 500 picture now on this machine is half a minute, and might probably with better programming be increased maybe to a second or something like that. And we have seen that this still means a month of work for the whole area. And if you want to put that in a plane that does it instantly, there's still some work to do. To be done. But, anyway, these are all also potential applications, and it's, I don't know, if the family only had like a little bit of more knowledge of what happened, this would be already of value to them in this particular case. Like even if one found another ghost chip somewhere, that would be then, anything that clears up what happened is of value. And the data from this was, in September, 3 months later, and if my search shows up something that tells them, well, this is how they got there, then this would be, even though in a situation with lasers and transponders connected to boats, still of value. Yes.
how effective is camouflage? So you could go buy at a hunting store against a program like this.
I just heard this joke. They painted a car with camouflage and then they couldn't find it. No, I don't know. I mean, I have no idea. This is just pulled out of a hat in a straightforward application.
Could you take the original and paint camouflage on his body and then rerun it and purposely try to confuse the program or the algorithm?
I guess I'm just wondering how close camouflage is to the actual natural.
Well, suppose he wore a short shirt, let's say, and had exactly something like this.
Even a little bit.
Yeah, right.
Or
I mean, then
you
would still have very much. So
A ghillie suit.
as soon as you have some surface, the rhinos can be discovered because they are flat and have surface as in the tree. And I don't know how good the camouflage is. I don't know. I mean, if you wore a fur or something like that, then yes. Painting it, you would still have a different illumination or something like that. You sure would have a difference in the texture.
Do you know how reflective surfaces work, like mirrors, in regards to how the process is?
No.
Okay.
Probably I don't understand the question.
If, I don't know, if an entire ship deck was made up of mirrors, how that process is in like satellite imagery.
I see. So if that happens, reflective surface means you see the particular light that is reflected from the sky to the camera, which is mostly sky. And it would probably be different than the sea surface, which is reflective if it's completely still. And I have some pictures for that also. It works very well.
So because it's diffusion of the
yeah,
light.
because it's a constant function.
Okay.
It is the roughness of the sea. And they talk about this in the articles. The rougher the sea is, that the more the wave crests form shapes on the order of magnitude of the boat's size. And it's not only the shape, and then it's so hard to distinguish it from the shape because the shape is so much alike. So it's reasonable to just first look at everything. And yeah, sometimes you just have that white spot there, and you just don't know. Anyway, thanks for listening.
Is the family